Okay, welcome back. So, on the last three videos of this series, it was about um, we do a revision in matrices. The first one, it was about transposed matrix. The second one, it was about the determinant of a matrix. And the last one that we discussed on the last video, it was about inverse matrix. And on this video, we will discuss about inverse of transformation matrices. So we do these revisions because matrices represent transformation. And when we do the analysis of a robot, we do need to calculate the inverse of a matrix during the process. So you will see how this concept is applied in robotics context. One thing that we need to revise also is how to read these notations, because on the first videos that I have released on this series, I was using the word referential from the Portuguese language, and referential word, it don't carries the meaning in robotics context. And actually we have to say framework work or reference frame. So we will learn how to read these notations which represent a transformation, and also calculate these equations which represent the motion of the robot, the motion of the arm, the hand of the robot, and the end effector. So this equation represent how the robot are moving around. Okay, so let's see. This first notation is read this way: the transformation of the reference frame A, E, in relation to a reference universe. Okay, so let me introduce to you these frameworks. We have this framework, which is a reference, universe reference, and we do the transformations having this one as reference, since we need coordinates to pass to the end effector, so it can do the drill on the workpiece. So this robot, it has a controller, and we storage the coordinates of each transformation, so the robot can localize itself and do the job. So we have the reference frame R, which is from robot. We have the reference frame H, which is from hand. We have the reference frame A, which is the end effector, and we have the reference frame P, the piece, and that is the workpiece, in which the end effector with its tool is going to be a drill. So the transformation of the end effector in relation to a reference universe is equal to the transformation of the reference frame R in relation to a reference universe times the transformation of the reference frame H in relation to the reference frame R times the transformation of the reference frame A in relation to the reference frame H, which is equal to the transformation of the reference frame B in relation to a reference universe times the transformation of the reference frame A in relation to the reference frame P. So that's how we read this equation, which is described how this robot is going to move around to do this job of to drill on this workpiece. So to guide me, I will use the text of the book. So I will just basically read what is says. So let's suppose that this robot are moving on the direction P. In order to do a drill on this workpiece P, and the position of the base of the robot in relation to the reference system U, and this is a reference system, and this means that we have coordinates right here that we can write for this other reference frame. So we do write equations based on this reference system, and this way we can track and notice that is important to track the base of the robot, which is fixed, the arm, the hand, and the effector, without miss the position. And this reference system U is described by a reference frame R. The hand of the robot is described by a reference frame H, and the end effector is described by the reference frame R. The position of the workpiece is also described by the reference frame P, and the localization of the point in which the drill is going to be done can be related to the reference system U, and this by two independent paths. One is from the workpiece, and the other is from the robot itself. And with this description, doing this analysis, we write this equation. So this equation described all this that I have just read. Right here, I have just write what I have said to you, which is on the book also. And we need to solve this equation which tell to us how the robot will do this job. And as I told to you, each of these notations, they are transformations. And transformations are represented by matrices, which contains coordinates for the robot like angle, and now you have to remember that we have rotation matrix, translation matrix, and this matrices contains coordinates which describe the initial position and the final position, if the robot is going to do a 90 degrees or a 45 or any angle. So we use inverse matrix to eliminate some of these transformations. And as we saw on the last video, when we do the multiplication of a matrix by his inverse, we got the identity, and we can do an analogy with 1. So let's apply this. I'm gonna copy this and paste. And now, right here too, because you will see that what we do in one side of the equation, we have to do on the other side, which is a basic concept. So if we do multiply the transformation of the reference frame R by its inverse, we eliminate this term of the equation. And as we are doing, we have to do on the other side also. And right here, to eliminate this term, the transformation of the reference frame E in relation to the reference frame H. So we are just left with the transformation of the reference frame H in relation to the reference frame R. And doing this side also. And with these operations, we simplify this equation. And have in mind that transformations represent how the robot are moving around. Keep this in mind. It describes position, initial position, final position, angles. And now you see why we revise about inverse, because we are doing the analysis of this robot arm in order to find the path in which this robot will do the job of a drill on this workpiece. One thing that I have missing is the -1, which is not a exponential, is a superscript, is the inverse. And this way we can eliminate these transformations. I was almost forgetting this, missing this important detail. And we have this property, the transformation of the reference frame R in relation to a universe reference. Its inverse is equal to the transformation of the reference universe in relation to the reference frame R. And this property allows us to rewrite this equation without this -1 superscript. So we can think on the path of the robot more easily. And this is the entry for kinematic of robots, since we are describing the motion of this robot, the motion of the arm, of the hand, of the end effector with equations, with transformation equations. Okay, and he keeps saying that actually he gives us a task and asks to us to calculate the inverse matrix of a rotation matrix, and it guides us to the appendix A. So on the next video we will do the inverse matrix of a matrix with order 3. On the last video we saw how to calculate the inverse matrix of a matrix with order 2, a matrix 2 by 2, and I said that for a matrix 3 by 3 and more larger is different. So on the appendix A we will see how to do the calculus of a matrix 3 by 3, and after this we will solve this example on how to calculate inverse matrix of a rotation matrix. And as I'm saying, this is an entry to the kinematic robotics. So we are analyzing the kinematics of robots, which is how the robot move around with his arm, his gadgets, the hand, the end effector, whether this robot it has 2 or 3 links, And for now, that's all. And see you on the next video. Thank you.